Okay. Hello, everyone. I am Junepyo and first year in telecom party. So today I'm going to introduce the paper which title is Heroes, Lightweight Federated Learning with the Neural Composition and Adaptive Local Update in Heterogeneous Edge Networks. Today content will be introduction, background and motivation, purpose frameworks, performance evaluation, and conclusion. So, okay, federated learning continues to evolve. It carries significant potential to advance edge computing capabilities and facilitate intelligent applications across diverse domains. However, it is difficult to implement efficient federated learning in practical edge networks due to resource limitations. There are three limitations for it. First, edge clients often have limited computation capabilities. Second, the communication resources are also scarce in edge networks. The last, the frequent transmission of large number of parameters will strain the limited network bandwidth. To address the issue, this paper suggests neural composition techniques, which approximates each model weight as the product of two rank tensors named neural basis and coefficient. A detailed explanation about neural composition will be provided in the next session. So, okay, despite resource efficiency, the neural composition technique will encounter some problems in the context of the federated learning. Firstly, the flank only aggregate the coefficient with the same shape. As a consequence, the coefficient of specific shape is only trained by the clients with the corresponding computation power, which may be insufficient for global model convergence. Secondly, the edge clients are equipped with the different hardware, thus their capabilities may vary significantly like client heterogeneity, which possess a great impact on training efficiency. Therefore, this paper proposed a new federated framework called Heroes to address the challenging issue associated with the neural composition. Firstly, they propose a lightweight federated learning framework called Heroes, which overcome the challenges of resource limitation and client heterogeneity. And second, they design a greedy-based algorithm to adaptively assign the proper coefficient and local update frequency. So the results reduce the traffic consumption by about 72.05% and provide up to 2.97 times speedup for the training process. In this section, I will introduce the key concepts necessary to understand this paper. First, I will talk about the federated learning briefly. The federated learning is a distributed learning method designed to train large amount of data generated locally and update models on local nodes. Clients use their local data to train the models and send the resulting model parameters to the server. The server then aggregate the parameters from our clients and send the updated model back to the clients. Next is neural compositions. The core method proposed in this paper. In federated learning, to make full use of the limited resource, it is essential to adjust the complexity of the local model for each client based on its resource budget. As we all know, the weight in deep neural networks used in federated learning are usually over-parameterized. Therefore, this paper utilized the neural composition of Planck, introduced the other paper to reduce the size of parameters transmitted from client to server while improving accuracy. In deep neural networks, each layer's weight can be approximated as a product of two ranked tensors, named the neural basis V and coefficient U. As highlighted in the first red box, if W is supposed to be a convolution weight, the tensor of the single layer weight can be represented as k squared times I times O, where k denotes the kernel size, I is input channel number, and O is output channel number. As shown in the second red box, the convolution weight W can be approximated as the product of V and U through low-rank tensor factorizations. And then, as indicated in the third box, the tensor of W sub P will be represented as K squared times PI and PO. So far, I have explained the basic neural concepts, neural composition proposed in Planck. Now, I will enhance the neural compositions proposed in this paper. Looking at the first blue box, we can see the original tensor size of the weight, K squared times I times O, is reduced through the low rank factorization, where the output channel number O is replaced with the low rank tensor R. Now, imagine the parameters are unfolded as shown in the second blue box. At this point, we can represent the parameters as R times P times O. The uppercase P represent the complete coefficient. And next, as illustrated in the third box, we select the reduce the coefficient, denoted as a reduced coefficient P, denoted as the lowercase p. Which ensures the square root remains an integer. For example, if the reduced coefficient p is set to 2, the 4 blocks are selected, like in this figure. The selected blocks are always the least trained ones. In this case, block trained 6, 5, 7, and 8 times are chosen. Finally, as shown in the first box, the selected reduced tensor allows to obtain 2 with weight. As shown in the table once, when comparing with the model pruning and original neural composition proposed the other papers called the Planck and the enhanced neural composition under the same traffic and time constraints, the enhanced neural composition demonstrates a significantly higher accuracy at the same traffic at the same time. Next, let's discuss, I will tell about the other main contributions called the adaptive local update. In traditional federated learning, considering the heterogeneity in computing capabilities among the clients, stronger clients must wait for weaker clients to complete their computation for global aggregations. As a result, the most powerful client often experience significant amount of idle and wasted time. So they designed the greedy-based control algorithm to adaptively assign proper coefficient and local update frequencies for heterogeneous clients. The adaptive local update algorithm proceeds in the following four steps. The first algorithm determines the model width for each client and second algorithm select the fastest client with the least completion time. And third, algorithm determine other clients' local update frequencies based on the fastest client's completion time in round H. And last, the parameter servers and the global basis V reduce the coefficient U hat and local update frequency tau to each participating client N for local trading. As shown in the figure, applying this adaptive local update algorithm ensure the stronger clients utilize their time or efficiency, significantly improving resource efficiency. Now I will explain how the method discussed earlier were applied in their research in this paper. Their proposed framework can be divided into the three main components. The first thing is tensors and frequency assignment, local training, and global aggregation. First, I will explain tensors and frequency assignment. The parameter server first determine the model width P for each client N in round H. Then here select the coefficient P coefficient blocks with the least total update times as the reduced coefficient U hat. Finally, using the proposed algorithm assigns an appropriate local update frequency, the tau, to each client N by the algorithm. The second is local training. In round H, each client N first download the latest neural basis V and the reduced coefficient U hat from the parameter server. And then client composes them into the local model X hat and X hat as a X hat and X bar represent the updated local model of client N in round H. Then X bar is decomposed into the updated neural basis V bar and U bar. Last is global aggregations. In round H, upon receiving the updated neural basis V and coefficient U from all the participating clients, the parameter server performs global aggregation to obtain the latest basis V H plus 1 and coefficient U H plus 1 for the next round of training. For neural basis, HEROES directly averages the updated one from all participating clients. For coefficient, HEROES perform the blockwise aggregation. In other words, for the coefficient, the aggregation is performed by collecting the set of clients that train the specific block during the round H. I think that the explaining about the algorithm is very long. It's taking very long. So instead, I will use a figure to demonstrate the proposed framework. For example, there are 4 heterogeneous clients who participate in training, like a smartphone, laptop, and powerful PC, and they divided into 3 levels by their computation power. Here select the one coefficient block for the weak client 1 and 3 and 2 blocks for medium client. 2, the powerful client 4 utilize all the blocks. To ensure sufficient training for every block, the selected blocks are the least trained ones currently. Heroes assign different local update frequencies for these 4 clients to balance their completion time. For example, the weak client 1 trains the model much slower than powerful client 4. So as a result, client 1 performs fewer local iterations to elevate the straggler effect, while client 4 performs more local iteration to make more contributions to the global model. In addition to the balance of a client completion time, the balance of coefficient blocks total update time is also considered for the determination of each client's local update frequency. Before telling the performance evaluations, I will only present a few meaningful experiments results from the paper. The data set and the model used in this paper include Cypher10 with the full layer CNN and ImageNet with the LizNet and Shakespeare with the RNN. However, in this presentation, I decided to exclude the result for Shakespeare dataset and the corresponding models because the result of Shakespeare dataset is not significant. So, yeah, okay. And additionally, the baseline method they use for comparison include bed average and ADP, hetero FR, and blank. First, about the training performance. Heroes takes 1,375 seconds to achieve an accuracy of 70% for CNN on Cypher10 and 40,000 seconds to accuracy of 64.36% for ResNet on ImageNet. These results demonstrate that Heroes outperforms the other baseline method. Next is the impact of the client heterogeneity. The average waiting time in Heroes is only 2.86 seconds when training a CNN on the Cypher10 dataset, whereas other baseline methods take more than twice as much time. Similar results are observed for ResNet as well, demonstrating the efficiency of Heroes in handling client heterogeneity in computational capabilities. Last is resource consumption. Heroes significantly reduce both time and traffic cost. For instance, to achieve 50% accuracy on ImageNet, the traffic cost of Heroes is 70.81 gigabytes, whereas the other baseline methods require much higher traffic costs. So in this paper, they proposed the lightweight federated learning frameworks called the Heroes, and they try to address challenges of resource limitation and client heterogeneity by proposing enhanced neural compositions and adaptive local update. So this is the end of the presentation.
In the experiment, where was it a sequence experiment or asynchronous?
Because in this paper they suggest the local adaptive algorithm, so the result will be must be the synchronous.
Okay.
I just have a general question. So you were interested in this paper. How will you use this in your work? Do you plan to have some improvements on?
I'm trying to find how can I compress the model weight, because this is very burdening communication. So yes, this is why I select this paper. This paper suggests how can we reduce the size of the parameters and how can we reduce the communication cost in federated learning.
So you also consider like combining these techniques with, I don't know, sparsification or other compression techniques, or you are planning to improve this, try to improve this?
No, I just wanted to refer the one method as one of the techniques. So yeah, because it is more close to about the model compression or pruning the model. So it is not my specific major. So yes.
Other questions about So thanks again.
Thank you.